show.
Demonstrating what happens when you try to route between two nodes in this network, and you see that it basically bounces all over the place. Greedy routing simply doesn't work.
Because you have none of the dynamic of the fact that I'm getting closer to somebody doesn't make me more likely to know them here. So the greedy routing, in fact, makes no sense whatsoever, because the whole thing with the greedy routing is we want to get close because that'll make it more likely that we find someone who knows the person. But here, routing greedily is just really the same as a random walk, because we're just bouncing around randomly until it does run into somebody who knows the destination.
Okay, so just for the purpose of illustration, we've taken one node in this network and we've highlighted the other nodes that it happens to be linked to. Since this is just a random distribution, you'll see that these links are all over the place. There are very few short ones. There are a lot of really long ones. This is not the kind of thing we would hope to see in a small world network. Now, what we're about to do is apply our algorithm, the swapping algorithm, to this network in order to rearrange the positions of the nodes in this network, again, without changing who they're connected to or not connected to, just changing their locations in order to try to get back to a small world link distribution. Now, this algorithm is completely decentralized. It can be implemented in a completely decentralized way. In fact, we have implemented it in a completely decentralized way. In freenet, we'll talk about that later. But the goal of this algorithm is to take a bunch of people. It knows who is connected to whom. It has no concept of where these nodes were originally. It's got to try to rearrange them in order to get back to a small world network. And here we go. So the algorithm is running.
So you can see two things happening now that you should be aware of. The first is that the histogram here starts to look more and more like it did originally, with many more short edges than longer, whereas we did not have it. And the other thing, of course, is that the green one, which had really long rays coming out of it, is now being rearranged so that it's getting closer to its neighbors, whereas before it was very far from its neighbors. It's finding a way to send in around them. And of course, also, you can see that the network itself is beginning to look more like it did originally than just the jumble that it was when we had rearranged it.
Okay, so we keep iterating here. It'll stop in a second. This is the algorithm that we will use with freenet in order to assign these identities, these locations, which in freenet is basically a very large number, to peers in the network in order to reverse engineer which peers are closer, in some sense of the word closer, that somehow maps onto social relationships, such that we can greedy route through this freenet small world friend-to-friend network in an efficient way. Okay.
There's one. Show the route as well.
Yes. Okay. And as you can see, we try to. This is actually routing between the same two nodes that we did the initial route between. And you can see that these nodes now have a different location. They have been moved. Our algorithm hasn't got back to the same configuration these nodes were in before. However, it has achieved a small world link distribution, and as a result, you can see that it's able to route in a pretty small number of steps. So the algorithm has succeeded. Okay. We'll upload this. This is just Java, a simple Java thing we hacked up yesterday. We'll upload it to the freenet website so that people can play with it. Okay.
So just to establish now that this demonstration we did is not the only indicator we have that this algorithm actually works as we'd like it to. we're just going to show some results from bigger simulations, where we've done simulations of very large networks rather than this sort of 225 node tiny little network that we did up here. And so I'm going to compare the random search, which is just walking around randomly looking for someone, with the way a greedy routing would work when the network is generated, which is always going to be very good. And then we're going to look at our algorithm, how close can we get back to the original thing after doing about 2,000 iterations per node of the algorithm. And the successful number of queries within this log squared of n number of steps is you can see that when you're doing a random search, as you'd expect it, as the size of the network grows, and I believe it grows up to 512,000 nodes here, you can see that random search simply can't be successful within that number of steps. We're only talking maybe 100 steps at most, whereas the greedy routing really always works. You can see the green line, which is just up at 1, because the dynamics there really work. If you have generated a network with these type of small edges, you can really just find where you're going. And then going from a screwed up network back using this algorithm, we can see that we've restored almost all the way up the success value. It's only at the very end there, at the 512,000, that we have some failures. And this basically just means because a network which is that large needs to run longer than my computer wanted to run it. And if we look at the length of the successful routes, we can see the same thing, that in the random case, it looks very bad. You have to take very, very long routes, and of course, we were only successful a very small amount of time, whereas in the good case, it's only less than 10 steps the whole time. Even up when you have 500,000 nodes, you're only taking 10 steps to find where you want. Whereas in the restored case, we can bring it almost all the way down. So we're taking maybe 20, 25 steps at most. And that was, of course, simulated data. And what we showed you in the graphical demonstration was also simulated data in the sense that we have, we've just generated a network that has this dynamic that we're looking for. And that then one would expect to be able to work because there's good mathematical reasoning why this algorithm should work on such networks. What about if we take data which is actually from a social network? So the first bit of data that we used this on was data we borrowed from Orkut.com, which is Google's social networking thing. And yeah, so starting from in here, we took out about 2,196 names and yeah, broke our EULAs. So and the people in the set had about 36 friends each, so it's rather dense, but. And as it turned out, we kind of, because we started with Ian, it tended to stay around the techies. So mostly Americans, but some Europeans. It wouldn't surprise me if there's somebody in this room who was, except for Ian, of course, who was in the set. I wasn't, though, so not popular enough, I guess. So, and it had this sort of degree distribution, which you might think is also true of social networks, which is that there were a few people, most people had only some 20 friends or something like that, whereas some people had very, very many friends, so up above 200. So, and one can then compare sort of, the best way previously, which has been suggested to search these sort of networks, is actually just to walk around randomly and hope that you find the person you're looking for. And of course, in this sort of network, I mean, in this case, because it's dense and because it's this degree distribution, random search actually works pretty well. You can, in about 43 steps there, you found 72%. So, I mean, I'm saying this is good, but of course, it's not practical. You'd never want to run something if you take 43 steps to find something. The latency would be horrible. But still, and I should go back. Our, on the other hand, was able, using the algorithm, running it for a while against this data set, giving people positions, and then routing based on that, we could do it in about 7.7 steps, 97% of the time. So we feel that this is rather indicative that this really does work on real social networking data. And just to show that it isn't about the fact that there were these stars who knew so many people, we clip the degree, by which I mean we don't allow anyone to have more than 40 friends. And then we can see that the random search suffers badly because it doesn't come through these people where it has all these friends. But on the other hand, our thing only increases by a couple of steps and the success rate stays the same. So it isn't really depending on such people.
Okay, so really what we've been talking about so far has all been about theory. And one of the, I guess, differences between us and other people is that we're actually putting this theory into practice. We have an open source project. We have implemented the algorithm we've just described in open source software in freenet, although so far it's still at a very early stage of testing. But building this kind of thing, making it practical is the real battle. Kind of getting the theory to work is, you know, it's not easy, but if the theory works brilliantly but nobody can use the software, you know, it's not a success. It's not a success for us. So when you're implementing this type of thing in practice, what are the problems? Well, how do you prevent malicious behavior? Anyone can join this system, provided, of course, that they know people that are already members that are willing to connect to them. But what happens if they try to disrupt the network in some way? What happens if, with this swapping algorithm, they try to abuse it by pretending that they have a location they don't have, or so on and so forth? How do we make sure it's easy to use? How do you come up with an easy to use way that people can find each other and agree to connect to each other and then tell their computers what their computers need to know in order to facilitate that connection? This is not a small problem. Look at something even like PGP is a good example, which came out years ago, which to software engineers it's pretty easy to use, but it never really entered mainstream usage just because it's not easy enough. And with freenet, the bigger the network is, the better, and we really can't afford just to be limited to a relatively small number of tech-savvy people. We need to make sure that freenet can be used by as many people as possible. And of course, there's another aspect of freenet is data is stored on, data is actually cached on people's computers in the network. Okay, so just breaking down each of those. What are the dangers? Well, if you have a certain identity, a certain position in the freenet network, if you get to choose, that will determine what information is cached on your computer. So if you can choose your identity, you can actually have an influence over what data people ask you for, people try to find on your computer. And so if you want to censor that data, then it places you in a position to do that. So we need to think about how it may never be possible to make that, to defend against that kind of attack 100%, but there are steps that can be taken to make it much more difficult and to make it require a lot more effort. And similarly, if you can also manipulate other nodes' locations in the network, it allows you to disrupt the routing process as well. How do we ensure ease of use? Well, there are a couple of difficulties here. Peers, in all peer-to-peer networks, it helps if people leave the peer-to-peer software running. But that is particularly true of this architecture because you may only be connected to 5 other people. If none of those people are online and you want to access freenet, you're not going to be able to do that. Now, of course, in some situations, if people are just going to switch their computers off at night or whatever, and there's just nothing you can do about that. But there are steps in terms of usability that you can take to make it easier for people or to make it more likely that people will leave the software running. And so we need to think about that from a usability perspective. Similarly, how do you introduce peers? In freenet, obviously, if you want 2 peers to talk to each other, they need to exchange their IP addresses on the internet, Additionally, we want them to exchange some